This section is about something called the goodness of fit test. We're going to use a new kind of distribution for it called a chi-square goodness of fit test. All right, you know what? I need to get this thing turned back to a drawer. There we go. So we're going to learn how to use a chi-square goodness of fit test, and what it does is it tests whether a frequency distribution fits an expected distribution. So you've got current data, you've got a pattern you expect it to follow the expected distribution, and we're going to test if it does it well enough to consider it the same or not. Now, what we're dealing with here is something considered a multinomial experiment. All right, a probability experiment consisting of a fixed number of independent trials in which there are more than two possible outcomes. Okay, if you remember, typically a frequency distribution has several categories, right? 3, 4, 5, I'm not sure how many. And so you've got your categories here, and then you've got your frequency, right? And you've got a count for each category. And then maybe you have a relative frequency as well, whatever. Okay? Now, the probability for each outcome is fixed, and each outcome is classified into categories. And then, this is called multinomial because when there were only two, we called it binomial. When it's more than two, we call it multi. All right. So a chi-square goodness of fit test, like I said, is used to test whether a frequency distribution fits an expected distribution. Always, the null hypothesis says that the frequency distribution fits the expected distribution. In MyLabs Plus, usually they'll actually list out all the percentages of the distribution and say the null is that the frequency fits that pattern. And then the alternative is that the frequency does not fit that pattern. Now, a couple other details. I have some terminal or some sort of abbreviations they used. The observed frequency in one of these things of a category is the frequency for the category observed in the sample data, right? So this is typically the current situation where data is observed, and you have numbers then. You have a number then for each category, however many of them there are. Those are the observed, the O. The expected, all right, it's calculated. And the way we calculate it is this. The expected for category I is the total count of the observed data, right? Add up all the people in the current situation, the observed situation, and that's your N. There's your total count. And you multiply that times the expected probability, PI, for that category. So the expected freak for category I is the total observed count times the expected probability for category I. All right, so that's just some sort of terminology thing, the way they talk about stuff. Another little thought here to perform a chi-square goodness of fit test, right? The observed frequencies must be obtained using a random sample, and each expected frequency has got to be greater than or equal to 5. Well, each one of these expected frequencies has got to be greater than or equal to 5. The model doesn't work if it's not. All right, so going through some details here. The chi-square, like the T, has degrees of freedom, and the degrees of freedom is K minus 1. That's just up depending on what kind of calculator, whatever. You can use your table 6. I'm just going to use table 6 in this video. You can also use a TI-84 or Excel if you wish, but I'm just going to use the table. And finally, here's the test statistic. We had those O's and E's above. We'll come back and look at more about how this is calculated later, but here's what it is. The chi-square is take the observed for each category minus the expected for each category, square that, divide it by the expected. This is really the percent difference squared, kind of. Anyway, add them all up. Okay, now, here's an example that will follow partway through. Tax prep company wants to determine the proportions of people who use different methods to prepare their taxes. They want to test a previous retail trade association's claim concerning the distribution of proportions of people who use different methods, right? So there's some prior claim with the distribution, okay? They're going to use this goodness of fit test to check it out. So they do their own data collections, hire somebody to do some surveys, whatever. Here's what they get, right? Total count is 300. and their categories: accounting, by hand, computer software, by friend or family, tax prep. All right, the categories for the observed and the expected have to match. So here's the observed is actual physical counts. Here's the expected from the prior survey. Here's the expected percentages. Now the prior survey is going to be in percentages like this, okay? So they give us that. The first step is always, right, you'll notice that the null hypothesis, HO, the distribution of tax preparation methods is, and it just lists out in words, pretty much in a sentence, all those percentages listed in the expected column, right? And it says this is the claim. And then the alternative just says that, hey, the distribution of tax preparation methods differs from this. Okay. Now you put all this in a table, this is what you get, right? We've got our categories down here. Here are our percentages from the expected distribution from the prior study. Here's our counts from our current study. They add up to 300, right? The current counts add up to 300. Now, so these you just write down for given. You have to calculate the expected, right? And the expected for each category, right? It's the total count of 300. See, times the 0.24 from that category, 0.24, 0.24. Total count of 300 times the 0.20, which was the 20%. Same thing all the way down, right? At the end, total count of 300 times the 0.15. These are all, if you wanted to check them, these should also add up to 300. They do. Okay, so that's how you fill out the table. Now, if you're going to use the TI-84, you hit Stat, arrow over twice to pick tests. Then you got to arrow down a bit, and it's down a ways, and you want to find the one with GOF in it. And what you're going to have to enter, it's going to ask you to put the observed frequencies in and the expected frequencies, and then it will do the rest. Okay? Now, so there's a TI-84 built-in function. If you really want to use your TI-83, here's a video about how to do it. I'm going to suggest that you either use the TI-84 or the Excel document that I have provided. So I'm going to use the Excel document. It's going to work every bit as easy as the TI-84. I've pre-made a bunch of stuff, okay? So to find the Excel document, it is in the course content area in Blackboard. If you go out there, you will see that there's a goodness of fit, chi-square goodness of fit document out there. Now, let me see how much time I got left here. All right, I think we're still good. Here's an example straight out of MyLabs Plus. It's pretty typical. Survey was conducted 2 years ago asking college students their top motivations for using a credit card. To determine whether this distribution has changed, you randomly select 425 college students and ask each one what the top motivation is for using a credit card. Can you conclude that there has been a change? In the claimed or expected distribution, use alpha equals 0.05. Now, one thing I'm going to say here is a little bit odd about the way they do the wording. Since we're talking about that there's been a change, okay, the alternative is going to be that it differs. Really, the alternative is going to be that it did change. Okay, so it's not at all obvious, but you'll see they follow that pattern pretty consistently. Now, what is the null? Well, the null is always that the new data follows the given distribution right here. If you see it, the distribution of motivations is, and blah, 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 blah. It just lists all these. And that's always the null. The alternative is that distributions of motivations differs from the expected. Okay. Now this one here, because it talks about if there's been a change, right? The alternative is that it differs. Okay. Now, next we have to do the critical value. Okay. Now these are all going to be right-tailed, by the way, because what's happening actually is that if they're the same, right? If the current data matches the old data, the differences are going to be small, and that chi-squared number is going to be small, close to 0. If it's big, so what's happening actually, the chi-square distribution, it's not symmetric like the ones we're used to. like the ones we've been doing. It's more like this. And so what we're saying is the rejection region will always be out here, because if the number's too big, if the chi-square number is too big, it means that they're too different to think they're the same. Okay? The bigger the chi-square number, the greater the difference between the observed and expected. That's the way I would say that. Now, coming back over here, we have to calculate our critical value. All right, so our alpha, I think, was 0.05. Yes, 0.05. And we're going to need our degrees of freedom. Now, I talked about that before. My degrees of freedom is the number of categories minus 1. There's 1, 2, 3, 4, 5 categories. So 5 minus 1 is 4. Right? So degrees of freedom is 4. Our alpha is 0.05. All right. So degrees of freedom. Now, in the statistical tables document, it's also in Blackboard in the course content area. There's also there might be an INV chi-square on the TI-84. I think there is. But anyway, I'm just going to use the document. So I've already got it pulled up here. Let's see here. There's the chi-square table. All right, so here it is. There's the chi-square table. You'll note we had 0.05 right here. Our degrees of freedom was 4, so 9.488, right? 05 in row 4, 9.488, 9.488. Okay, now so what's going to happen, if it's bigger than 9.488, we're going to reject the null. Now we have to calculate the test statistic. To calculate the test statistic, we're going to have to come back up just a little bit. And we're going to have to enter this, we're going to use this data in the table. Okay, so if you don't already have it, pause the video, go over to the course content area in our course, find the chi-square worksheet. It's the second one in course content. I've added in there recently. It's right below my Professor Gibson's videos. All right, so pause it, go get it, come back, and then we'll do the next thing. Okay, so here is the spreadsheet. Okay, all you got to do is put in the numbers in the green columns. It'll calculate the rest. Actually, I've made this so this is slightly quicker and friendlier than the calculator. Everything else is a formula except in the green columns. I made 8 categories in case we need that many. I don't think we ever will. So the percentages here, 27, 23, 22, 8, and 20. 27, 23, 22, 8, and 20. Notice it adds up to 100 at the bottom. Then we have to type in our observed, 110, 98, 109, 48, 60. 110, 98, 109, 48, 60. Adds up to the 425 they gave us. Everything else is calculated automatically. Leaves the zeros in for the blank ones. 15.884. Come down here. 15.884 it is, which means we're going to reject the null. There is enough evidence to conclude that the distribution differs. That's it. I hope you found that helpful.